Thank you very much. Hi all, good afternoon. I take this opportunity to thank the organizing committee for giving me an opportunity to present our work we are doing at Philips. So I represent Philips Research India. I'm part of Philips Innovation Center, Bangalore. Uh, we have research centers collocated across different global locations. So, we have a research lab at Eindhoven, that is Netherlands, and we also have research lab in the US, Cambridge, and we have it in Russia and Germany, Hamburg, and many places. So we all work on cutting edge technology. So how we can really improve the lives of how we can really improve the lives and touch lives. Okay, so that's the motto. So with that introduction, I just want to introduce audience to the FAIR data station for federated learning. So in this talk, what I'm planning is I'm making it as two parts. One is about the FAIR data station, so about the data, the complexities involved in the data, and then how we can do a kind of a verification process, findable, accessible, interoperable, and reusable, and then put that data in that format. Otherwise, data is quite crucial. So whenever you really want to develop any machine learning or deep learning algorithms or models, what is really required is data. Otherwise, it's more like, it's a kind of a box where you chunk in, chunk out. The moment you give kind of a data which is incorrect, so the output also, the model representation may not be proper also. That's why the data is quite crucial. So when by seeing that data is so crucial, so what are the challenges to get these data in the right form? So that we are going to discuss. And the federated learning. So nowadays, the federated learning, why do we really require a kind of a distributed learning or learning from the multiple hospitals? So that we are going to discuss, because nowadays the law of the land has become quite crucial. So now with the introduction of a GDPR in Europe, and then FDA in US, and then even our Indian laws are getting very stricter. Like if someone really wants to take patient data outside India, they'll need a kind of a special permission. Without that, it is very difficult to take it outside. So then that is another challenge. How do we really overcome that? So that's where this kind of federated learning really helps. So in this session, you stop me at any point of time, and if the session is interactive, it's okay. It's very good for me, so that rather than kind of a more of a monotonous dialogue, it's more of a discussion. I welcome those discussions also. So suppose if the discussion goes too far, then we can really think of taking at the end. Okay. So with that, let me get started on the presentation. Am I audible? Is it okay? Everything is clear? Can you see my presentation?
Yes, sir. It's visible,
Okay.
sir.
Okay, cool. So in this, the agenda, the main topic I really want to cover is about the introduction for the data. Like the one I mentioned, right? It's about the challenges. What are the challenges we face in the data aggregation, data collection? How crucial the data is. So what are the strategies for it? So that let's go with some examples and see what is the type of data we really need. What is the strategies we can really come up with. And then I'm also going to talk about the personal health train concept. So this is very interesting concept where in the Europe, right? So this personal health train has become quite popular. Even the European government itself, they have really taken it very seriously. And then all the government is really supporting this health train concept. So what is this concept? Let's discuss more on that. And then the fair data station itself, how we can do a verification of it, and then at the end, how we can really combine all this and come up with kind of a federated learn. Okay. So now let me go back. Let me switch my gear with respect to the data, right? So what is you people must have already seen, right? So there's the of late that ImageNet has become kind of quite popular, because it really gave a very good result, and then it's kind of a path-breaking result. So everyone thought, oh yeah, it is really happening. So that is where the deep neural network has really taken a completely a different attention, and most of the researchers are trying out this technique. But if you really go and see what are the efforts is really spent on this image classification, ImageNet deal, right? So they use around 14 million images. So that has been hand annotated. So this is the kind of data what they've used to really get a very good performance, right, of more than 80, which is almost equivalent to on par with the humans, right? So that is where the problem is. Now we need to ask ourselves a question: do we have this luxury in healthcare with respect to data? See, because so in healthcare, it's a different scenario. If it is like a natural images, you can always go click on images, and then you can click on multiple images and object images. You can always get plenty of images to play around. That is not a problem. But when you really talk about the health data, patient data, what we really need is a kind of a disease data. Suppose your patient is suffering from cancer. If you really want to come up with kind of okay, I want to come up with kind of a lesion detection or lesion segmentation, lesion characterization. So then what kind of lesion we are really talking about? Are you talking about cancer lesions? So how many is it possible to get such type of that a huge data set with such a big sample size? That's again a question, right? So how do we really overcome? So that is one with respect to the image, and similar way with respect to other data sets also, right? With respect to, especially with health care, getting data is a bit tough, and also there are a lot of stringent strings attached to it. What are those strings attached to it, right? So, for example, when you really come up with a kind of AI model development, since you're all going through this data science course, so at the end you might be familiar with coming up with a designing AI model, and then how, and then to get more insight from the data. See, you can design an AI model, but that AI model is completely depends on the type of data sets what you have really used. Imagine a situation, you have come up with a data set where it really works very well for the Asian community, or example, it might work with the Indian population very well, and then and then it might do with China. But when we go to the West, where Europe, the European population, U.S. population, and African population, where the body morphism, the ethnicity plays a major role. The organ itself might be big, the lesion size might be big. And so those are the variations what we really need to consider when we really want to design an AI model. And I've listed few. Some of them are variation of a clinical practice. That means the way the UK system and the US system. At some point of time, I went, my wife is suffering from a rheumatoid arthritis. So we went to a rheumatologist, and he said, yeah, I have trained from UK. So the treatment methodology will follow the UK practice. And then we changed the doctor, and we went to the other doctor. The other doctor, he has completed his masters and post graduation from US. There he says, okay, my treatment is a bit different, right? So the clinical practice itself is different. So one fellow says, the UK person says that, oh, I want to go very aggressive. Whereas the other person, no, I don't want to go very aggressive. I want to analyze the patient, how patient is reacting, and then based on that, I'll just play around with the dosages and others. So that's one simple example where we can talk about variation of a chronicle practice. Then the practice itself will vary. So then the data, whatever you gather, the AI interpretation of that, it's a kind of a one variability. And then multi-geography, like as I was mentioning, right? So we need to really get data from the multiple the geolocations. Rather it can be Australia, US, Germany, all location we need to get the data. And then
The other thing is about multi-vendor itself, right? So for example, if you're really getting images, say CT images or MR images or PET CT images, so then again, for example, let's talk about the PET CT mission. So in that PET CT mission, what we really do, it's a kind of a gamma cameras, right? What we really put gamma cameras. So what happens? The patient will be injected with the fluorodeoxyglucose, and then wherever the metabolic activity is high. So since the nuclear traces are tried with the glucose, wherever there is a metabolic activity, so there the absorption of glucose will be more. The moment the absorption of the glucose is more, since the nuclear tracer is attached to it, the more photons will start emitting from the cancer location. The moment the more the photons are emitting, so then what we do, we build a kind of a gamma camera, a ring around that, and then we pass the patient inside that ring, and then we capture those photons and then form a kind of a 3D volume, and then we are going to visualize the cancer lesions. But the issue, what I'm talking about, is about the multi-vendor. So when you really look at it, right, the way they design the detector, the elements what they do use in the detector itself is different. For example, GE uses a non-time of flight signal, other one uses a time of flight, and then someone uses a gallium, someone uses silicon oxide. So the way the detector material what they use itself is different. The image formation from the multiple vendors will be different, and so that's another challenge, right? Then if you really come with the CT, there can be a kind of 64 slice CT and 16 slice CT and cardiac CT. There are plenty. There are a lot of variations. And then the reconstruction kernel itself, the moment you get the images, we need to reconstruct, and then there are different types of reconstruction kernels exist. It can be a bone kernel, it can be there's a lot of variation exists. That's with respect to the multi-vendor. So based on the vendor, based on the pre-processing techniques what we use, the image whatever we get will also vary. The image means the opacity values, the CT values. So then different reconstruction kernels we talked about, and ethnicity, like we also talked about ethnicity, and then ambiguity in annotations. Right now, whether it's kind of what we are really talking about is supervised classification, right? So whenever we discuss about the machine learning with respect to healthcare, we really most of the time we stick to the supervised learning. That because otherwise FDA won't approve, because the reason is the health data is quite crucial. So imagine if there is a patient, if even though the patient doesn't have a cancer, you diagnose that patient as a cancer, it's a kind of a false positive. Your ML algorithm model comes up with a kind of a false positive, and you're calling that patient, even though the patient is not suffering from cancer, you identify that and say, oh, there's a cancer, then imagine the patient quality of life for rest of the year, rest of his life. No, that kind of a fear will add that fear to the patient, right? So then that's quite crucial. So that is why always go with the supervised learning, where the doctors will mark the annotations, we learn from it, and then also we'll vet it with multiple clinical trials and make sure it is really proper. Then only we release it to the market. Even if you release it to the market, we never ever say that the CAD or a kind of a AI algorithm is the kind of a primary reader. It can only a kind of a secondary reader which can really support the decision of the doctors or the clinicians who are using it. So ultimate decision is from the clinicians, and they are going to say that yes, they can make use of this information. They are going to decide whether it's a kind of cancer or not cancer. By saying so, what is that is really important is the ambiguity in annotation. So now the other story of that is when you're really coming up with a kind of a annotation, right? So then the multiple doctors, what we do in order to get, for example, we give set of volume or a set of CD slices to the clinician, radiologist 1, radiologist 2, radiologist 3, and then each radiologist will mark that. Sometimes what happens, there is at the end of the day, we are all human beings, right? So we tend to do mistakes. So there are always chances that the ambiguity also exists between the two readers. How do we really resolve those ambiguities? That's also another issue. How do we really handle that? And then the clinical stage protocol itself. Someone really goes with the high dose, and one goes with the low dose. See, somehow I feel that compared to US or advanced developed countries, in our India, the clinical practice, right, sometimes should be very careful. Like the protocols what they use. So what kind of protocols they use. So now across India, we should also see. So most of the time, the vendors will support and help the clinical sites to come up with the clinical protocols. But sometimes what happens, the clinicians, based on their need, they will also modify those protocols, and they'll be introducing their own protocols. So that is where we need to be. Again, that's another variability that we need to really think through. That's about the requirements. And then if you really go to the data access challenges, so then, okay, now triple IT Allahabad, okay, so we say, okay, I want to, say, for example, you're a professor, you'll go do a kind of a clinical collaboration with multiple clinical sites, and then the intent is very clear that you want to design some AI models along with his students, right? So then, so it also depends on the clinical side. Some of the clinical sites say that, okay, I don't have resources. I can't give you the annotations. I can give you the volumes. I can give you the images, right? So then that's another challenge. So then how do we get the annotations? And then the ethical, I am not allowed to. So sometimes what happens, the hospital ethical committee is very important. If you go speak to any doctors, doctors are not allowed. So they need to put that study in the ethical committee, and they should get the ethical committee approval. Then only they can sign the contract with the institutions. And then the commercial, sometimes it is expensive, right? Sometimes some hospitals say, no, I have invested so much of money on this. So I can't. So then the data, for each data they might charge more. So those are all the other issues. And then the main and important issues what we really need to consider is regulatory, that is privacy compliance. The personal health information is quite crucial. Whenever you are doing any pre-processing, we need to make sure that data is de-identified from the personal health information. So personal health information can be kind of a age, name, sex, and a lot of other things. Sex, yeah, it's all kind of ambiguous, but there are other things. Sometimes for your analysis, you might require a sex. Then similarly, there are listed items in the personal health information. We need to make sure that the data is de-identified, and then only we can go ahead and process it. And on top of it, I was telling you, right, the personal data protection bill, it's there, it's in the parliamentary, it's for the approval. I think they have approved it. It's in the last leg of the approval. The moment they approve that, then taking data out of India, it's itself is difficult, right? So then how do we handle those situations? How do we really address the multi-geography type of requirements? And then the GDPR, FDA. So those are the things, those are all the challenges what we really face in the data collection. So in these kind of scenarios, how do we develop a model? That is a challenge and the question. Okay, so the one solution might be a different approach. So we need to come up with the regular way of working may not be feasible in these scenarios. So in that sense, what we do, if data sharing is a problem, don't share the data. If you can't bring the data to the research, you have to bring the research to the data. That means if AI model development is happening at the lab, so for example, IIIT Allahabad lab you are developing, and the way you are doing is you go collect from different clinical sites data, and then keep the data in your server, and then do develop a kind of machine learning models, right? That is not allowed because of the law of the land, and then a lot of issues, whatever we discuss. So in that scenarios, what we can do, why can't we do the model development at the hospital itself, or at the clinical site itself? How do we do that? So that can be an approach. So this approach is faster, better, and cheaper. So in that way, what we can do is we can also have a collaboration with the doctors, and then we can also involve doctors while developing the model itself. In that way, the acceptance of the AI model from the clinician community will also be better. And in that way, it's a lot cheaper and then better and as well as faster. So now, having said that, okay, we can really bring data research to the data. So how do we do that? So that's the next question, and then that's the problem. I am going to have some solutions. We can always discuss those solutions. Okay, so then the solution, whatever I talked, is about this personal health concept, train concept. This is a very nice video. Let's watch this video for a few minutes, and then this really gives you insight on how we can really handle these challenges. So let me know whether we can really hear the audio.
The personal health train's
Can you hear the audio?
main goal is connecting health data to make them more
Audible.
usable.
Sorry? It's
It's
audible,
audible,
right?
sir.
Thank you.
Personal health management requires increasing amounts of personal data. But today, this information cannot easily be used because the data are produced and managed by various healthcare providers, authorities, and more by citizens themselves. These stakeholders collect and manage their data in different ways, making the data hard to find and use. Furthermore, personal medical information is very privacy sensitive. As a consequence, personal health data cannot be used easily by citizens themselves, by physicians, and by researchers. The personal health train goes to the root of this problem by building fair data stations. Fair protocols ensure that data are findable, accessible, interoperable, and reusable. These data stations are connected by tracks, which are strictly secured and protected. Fair data trains are constantly monitored, and only trains with the appropriate validation may enter a particular station. To secure privacy, every data station has rules. Each data owner has access to his or her secured station and can easily request and control one's personal information. In addition, the owner can set rules for who can access the data and how it may be used. Communities with common interests, like patient societies, can choose to connect and organize their information through umbrella stations. With this access, a researcher can learn, for example, which cancer patients benefit most from novel therapies such as proton therapy. Or a citizen with a specific variant in his genome can be automatically alerted when new research results, insights, or possible risks become available. In this approach, the information is accessible for research, prevention, and education without the data ever leaving the station. With the personal health train, health data becomes available whilst individuals and institutions maintain control.
Yeah, that's the kind of a concept what I'm really talking about for this, the challenges. The challenges, whatever we listed and discussed in the earlier slide, that can easily be overcome with this kind of a personal health train concept. Now, we have seen this personal health train concept that's quite easy, but that quite cool and good solution. But how do we realize that? So what are the technology components that is really required to realize this, right? This is a kind of a hand goal, what we can really think of. And that is where, let's go one by one and then see. Like first, let's take up this fair data principle. So what is this fair data principle is all about, right? Fair, the findable, accessible, interoperable, and reusable. So findable means, so whatever the data you do, right, it's kind of a, it should be kind of a sufficiently have a rich metadata. So the moment data is there, so data should be associated with the useful information about the data itself. That is usually captured as a metadata. And then we need to have a kind of a unique and persistent identifier for each data set. So for example, when you really want to do data, when you really want to use a data for research purpose. So we need to make sure that it is data is de-identified. The moment you de-identify it, are you going to give a kind of a unique name for it? So what you need to say that, for example, you will get the data from Europe or US or India. So you need to have some kind of a unique identifiers to say that which global location is there and all that information, and that should be there in the findable and then accessible. So metadata and data are understandable to humans and machines. Data is deposited in a trusted repository. That means whenever you should repeatedly access the data for AI model development. So you need to make sure the data is kept in the repository and also trusted repository. What's the meaning of that? So there should not be any data leakage. So see what happens when you really go get the data from the clinical side. So in the clinical sites will be having a certain rules and regulations, some conditions on some certain conditions only they can give the data to the research. They say, okay, the data should be accessible only for IIIT Allahabad. It cannot be shared with some other institutions. If that is the kind of a clause they have put and given the data, you need to make sure that the data is not leaking or some other people unauthorized, without authorization they can access, right? So those are the things we need to really control. And then interoperable. So idea is, see what happens interoperable in the metadata. So for example, sometimes you can't come up with a kind of a machine learning algorithm to do a kind of a natural to do analyze get insight from the radiology reports. Let's take that as an example. Radiology report. See, for example, if you go in India, radiology reports usually in English, and US and UK it will be in English. For example, if you go to Europe, certain countries have their own language, right? So the radiology report will be in completely, either it can be German, French, or the language barriers will be there. So then, how do we really interpret that data? How do you make it interoperable? So that is one of the crucial thing which we are going to discuss in further slides, and how we can really make it happen, right? That is interoperable and then reusable. So whatever the data we really get, so make sure the licenses are in place and then accurate information exists, and then it's easily accessible, and then that is also reusable. So for example, if you really want to add more data to it and make sure that you want to improve the accuracy of it, and then you should repeatedly reuse the data, right? So those are the crucial things what we really need to address in the fair data. This is called fair data principles. Now, see, fair data principle has become so popular that in European Commission embraces the fair principles very well. So what it says is, whatever the projects funded by European Commission, they made a rule that all the data should follow this fair principle. So in that way, the fair is one of the important thing we should really consider. I think it should also be considered in India, and that way the data representation would be a lot better. So let's see what's the advantage of how do we really handle this. As an example, how do we really make this? Okay, let me stop here for a pause here for a while. So far, any questions or any comments or reflections? Feel free to share.
May I ask you a question, Professor? I'm Sasi Kumar.
Yeah, please go ahead.
Yeah. My doubt is about the error minimization issues in case of utilization of drone data, especially for agriculture scientists. How to minimize about it? Recently, I encountered an issue with in the process of minimization of error in drone data. A lot of filtration is happening, whether I use supervised or unsupervised learning methods in machine learning. Especially in the agriculture databases or public accessible databases, lot of filtrations is happening. How many, whatever may be the number of iterations we did for the purpose of collection of data. So how to handle this issue? This is one of the practical issue recently I encountered. I am a faculty from Geetam Hyderabad Business School, and my one more question that I raised in the chat box is about, especially in this type of public access databases, what was the commonality I observed, especially with my little bit of research about outliers. Lot of outliers are there. If I try to remove the outliers, what's happening? The authenticity of the data was affected. So how to handle this jigsaw issue in the data processing?
Yeah, that's really good. Professor, you are really touching on the AI model development itself, right? So how do we really make sure the AI model is really capture the heterogeneity of the data, and then at the same time we really want to hit a kind of a very good sensitivity by reducing the error, those things, right? Yeah. So that is again, it comes under the model development activity. What you're really talking about. So for that, yes, of course, the data is also crucial. So what we need to really do is, depending on the data, you may have to strategize your AI model development also, right? So selection of the tool. So what my suggestion is, see, whenever you really want to fix any problem, there are multiple tools available, right? You need to select the right tool to fix the problem. For example, there are bigger nails and smaller nails, and there are the hammers of different size. So you need to pick the right size of hammer to nail the particular size. So that's kind of a very generic information what I gave. But similar way, here in machine learning or deep learning, how first of all you need to see how you are solving, whether you are solving via deep learning network or deep learning way or in the machine learning way. And if you're really solving via machine learning way, probably you need to select the right set of features is quite crucial. So selection of the right set of feature is quite important. Sometimes some of the existing features may not be helpful. That is where the research component will kick in. So where you should be kind of a more innovative to make sure features are good. The moment you have a good feature, so then automatically your training will also converge, and then your error rate will also decrease. So it all depends, right? And then your second question about the heterogeneity, it also depends about the sample size, whether you have good sample size of those outliers. So the outliers are important, but do you have enough samples of outliers so that you can really consider those heterogeneity? So that the data collection is quite crucial. So probably you need to really focus more in those areas. Yeah. I think we can, if you have further questions, yeah, we can discuss at the end. So let's.
Thank you, Professor.
Thank you. Okay, so but yeah, that's a good question. So one of the challenges, what the professor also mentioned. So along with this, there's other challenges also. So here we are talking more on the data issues, and then the representations. So sometimes what happens when you really get a data, it can be kind of a clinical reports. Data means what? I'm talking more from the healthcare data here. Okay, it can be clinical reports. It can be DICOM images. Sometimes it can be radiomic features itself. That means, okay, man, I don't want images. I want features. So I want to put features as a data samples, data sets, right? And then patient monitoring data. So it can be a ECG signal, EEG signal, 1D signals, or electronic medical records, EMR, right? So scheduling data, all this information. But is there a way where we can really represent this data? So in one form, so that is called resource definition form. So in RDF, we can put we can represent, we can store different varieties of data in the form of a resource definition function. So what is this RDF is all about is nothing but triples. Okay, so this RDF is also more to do with the triples, where what we're really talking here is about the subject, predicate, and object. So here the subject is a patient, and the predicate is nothing but the diagnosis, and the object is about lung cancer. So now for the subject, predicate, object, so for the word diagnosis, there is also a kind of uniform resource identifier exists. Okay, so there are certain standard libraries, URI libraries exist. It can be a Snowmed or a Radlex, or there are different public URI exists. So probably we can use that and then represent in a kind of a very more generic way. In that way, your data would be represented in a very generic way, and then it would be interpretation would be a lot easier. So the advantage of representing this data in the unique way is also kind of finding a clinical pathways. Okay, so here the ontology, right? So when we really talk about the here, diagnosis is a relationship between a subject and predicate that explains how both data are linked And this is what we call ontology. So we also give a kind of a ontology, name ontology to these kind of a subject, predicates, and objects. So this is another area where ontology is also very good, where we can really represent the data, and it has a very strong hold on the data representation. And we can really come up with a different, way, the clinical pathways. I'll just show you how we can really do. So the moment it is there, so what we are doing is earlier it is diagnosed, then I'll replace the diagnosis with a kind of a URI. And similarly, lung cancer also has a particular URI in the RADLEX library. I'm just giving an example of a RADLEX library. We can use that. So this is a kind of lung cancer is represented by RID 45686. And then the other one is what we said is diagnosed. Diagnosed is represented in the RID 10394. So this is a kind of a standard URI. So what we are trying to do, we are trying to map this patient to the standard URI. In that way, already there are certain standard treatments available with respect to this. It is captured in the SNOMED and other things. So already treatment are available. What are the treatment for the lung cancer? There's also already a treatment available. In that way, what we are doing is we are standardizing the treatment, right? So it can be, this is what I said, right? The DICOM images. So images also, DICOM images is also standardized. And then this patient images are represented in the form of a DICOM. And then we can also represent how the images are associated with the cancer. And then one example I was telling, right? So for example, if you really see that lung cancer, this is a kind of an ontology, what standard ontology that exists. In this lung cancer, what we are really seeing is a different subset, type of cancer. It can be a mesothelioma and primary lung. It can be a primary lung cancer or a secondary lung cancer. It can be a non-small cell lung cancer or a small cell lung cancer. And then what are the different type of treatment that exists for this type of lung cancer? It can be surgery, radiotherapy, chemotherapy. You know all these, right? Surgery means what we can go resect that particular cancer organ, or it can also irradiate with a high beam and then burn that cancer tissue. And then chemotherapy is really like a very painful one. No, see, so what we are trying to do, we are trying to inject the drug for the whole body itself, right? And then yeah, there are a lot of side effects, but nowadays there are also targeted therapies happening. Suppose what they do, they inject the medicine to the particular site. So that is where this interventional radiology is also picking up very well, where we can go to that particular area and then we can also inject the drug. In that way we can kill the cancer cells. And there are different clinical pathways also exist. So in this sense, what we are doing, the moment we are mapping this patient to a standard ontology, so already a kind of a standard set of procedure exists. So in that way, doctor can also select a kind of a clinical pathway that exists, right? So, and then based on the affordabilities, cancer treatment is quite expensive. So affordability and a lot of other things. So people can select the particular clinical pathway. So that's where it would be very quite useful. That is the strength of this kind of ontology. Let's try to see how do we build this ontology from reports, right? So like as I already mentioned, the steps followed to build a report ontology is we extract semantic information from. So here we have used one of the publicly available data, that is mimic reports, mimic database, and then represent them as ontology structure. So existing ontology from SNOMED, RADLEX, LOINC, so three types, and there are multiple, there are other ones also exist, are used to link medical finding to ontology structure. Then the RDF is used to make triple subject predicate object, where subject is the URI, example I gave, right? And then we can describe the relationship between them. And then we have also given an example of a lung cancer. So one of the, this is what we really saw, right? It can be kind of a hormonal therapy, active surveillance, all those things. So what happens? How do we really get? So this is kind of a typical one, radiology report. What you can really see. So this is the radiology report from this. You can do the natural language processing. So I'm not really going deep into that natural language processing because my today's topic is a bit different. So where we are really talking more on the how we really plan the data and the federated learning concept. So that's why I'm not really going deep into this. so that we can do it later. So once we have this report, we can always extract the information from it, and then we can represent. So this is the information what we really extracted from the lung cancer. It can be a mesothelium, and then small lung cancer, and then adenocarcinoma, squamous carcinoma, like that, right? And then what we do, so we map that to the standard ontology. It's already standard ontology exists, so where exactly it maps, that we can really see. So, and then, for example, this is a mesothelium, non-small lung cancer, see, this is a 254, right? So this is also attached to 359. This is adenocarcinoma. The report, whatever we extracted, this is also related to 3591707. That is nothing but adenocarcinoma. And then that way we can really do a kind of a mapping. So that way it is quite useful. Right? That is about one of the way where we can really represent the data. The moment you represent it, you get the data, it's all in the kind of a graph. So nowadays the knowledge graph is also picking up very well, right? So this knowledge graph is also related to the ontologies. So the moment you have data in the form of ontology, you can also put it in the form of a graph DB. Is nothing but it's kind of a database which can really holds this data in the form of a graphs. For example, the one what you really see is a kind of a clinical data. So we have this clinical data where there are patients, the smoking history and all other information that we can really represent it in the form of a ontology. And then you can see is a kind of a graph, right? So we can represent it that in the form of a graph. And this is another image where you have header information. We can also represent that in the form of a graph here. And then once you have this, you can copy, or you can store all this data in the form of in GraphDB. And then what you can do is we can also do a Sparkle query. You can get the data. The other important thing here is the moment you get more, you can also develop a kind of a classifier for this, and then you can also store that classifier information or kind of a machine learning information as another column, and you can also do a simple Sparkle query, and you can get all the information out of it. So this is one of the demo what I really want to see. I want to show you. See, this is a kind of the data what you really store in the GraphDB, and these are all the different patient data what you see. And the moment you get this, you can also get the visual graphs, and then you can also drill down to the data set itself, like patient, which clinical site, what kind of disease, and all the information you can always do. The here what I'm trying to tell you, or what trying to show you is the strength of this ontology, strength of this knowledge graph, how we can really represent, how we can really connect the data, how we can really connect with respect to the clinical pathway. In that way, the connectivity is quite good. In this kind of the ontology representation of the data. And then we can also store them in the kind of a graph DB. So the one what you're really seeing is the kind of the output of it, and then we can also export it as a CSV file. That is about the GraphDB. So finally, when you say, okay, you spoke so much, what's the advantage of it? Where is it fail? Yes, I'm coming there. So the one what I really showed so far is we are storing all the data in the form of RDF, and then we are storing that RDF in the GraphDB, and we store that information in the computer, and then we do a Sparkle query. So in that way, it can be findable, accessible, interoperable, because we are also representing this in the form of the ontology, where the image, you saw that the radiology report. The radiology report, we converted that into ontology. So radiology report can be of any language. We can convert it into ontology. In that way, it becomes interoperable, and then we can also do a Sparkle query, and in that way, we have done a verification. So the one what you really see is kind of a fair compliant. So that's how we can really make the data more fair compliant than verification. Now, I'm changing the gears now. I'm now moving to the federated learning, right? So what is this federated learning is all about? How we can really use this fair data, right? So in this federated learning, the concept is very simple. So what we are trying to do, it's more of a distributed learning. What we do, data stays in the hospital. Only the model weights will be shared across the different. There will be a server, and the multiple nodes are nothing but hospitals. So what we do, each hospital will be having will be training, and then the models weight only be transferred to the server, and then that's where the aggregation happens, and again it will percolate it back. So how that learning happens? So that is where one of the example is. So suppose if you are coming up with a kind of a support vector machine or kind of hyperplane, right? Suppose there are two features. How do we really learn? Right? For example, we get data from hospital 1, 2, 3, 4 different hospitals, and then the moment we get this, the hyperplane will also vary, right? So then based on that hyperplane variation, we can also see we are learning from the multiple hospitals and then come out with a common classifier which really supports data from all the hospitals, right? So then the other concept what I was really telling is these are all the fair data stations, and this is the main server, right? This fair data station is nothing but it's a kind of a computer where we are going. It's, for example, we'll take one example, right? Tata Memorial Hospital. This is one Tata Memorial Hospital. We have a fair data station. Another one is about Healthcare Global Hospital in India. Another one is a Maastricht University from Netherlands. So what we do, so doctors or radiologists who are in Tata Memorial Hospital, they'll identify some cases, they annotate and they keep it ready. And similarly, all the other hospitals. So here the data is prepared and kept. And then what we do from the main server, what we do, we server send the initial weights and scripts to the different fair data stations. Suppose the initial model, whatever you have built, that will be stored, sent to the fair data stations, and then the training happens at each station, and then once the training happens, so then the weights will be sent back to the server. So in the server, what we do kind of aggregation. So then we can have a different strategy. Either we can have a simple averaging of weights, or we can have kind of a weighted average, and we can design our own way. So it's all up to us. Okay. So once we have aggregation strategy, then we can always push back data, and then that's how that iteration happens. Where from server to different fair data station, the to and fro of exchange of weights will happen, and finally the weights will get generalized, and then once that is there, then there's the main server, whatever the model X is, so that we'll take and then we implement it we use that as an AI model. In that way, what is that we have achieved? Data, we are not taking any data out of the hospital. Data stays in the hospital. Only the model weights will be shared. And in that sense, it will be, we are more compliant with the law of the land, where we are really not taking any of the data from the hospitals. Right. And then to do this, we have done some kind of a prototype algorithm. So where we have realized the kind of inception network, where we did a kind of the bleed classifier here. So it that stroke classification, it is a kind of a brain image. We have done a stroke classification, and then we also did one of the other application. What we really thought is we did is about the liver classification. So the liver classification also, the segmentation also we did via this federated learning. And finally, we did a kind of a comparison also, right? So for example, when you really see this, right? So the number of nodes, the liver segmentation and strokes classification. What we did, so we did a kind of a multiple node analysis and then the combined data. That means in the combined data, we have not used any distributed learning or federated learning, where we have given all the data and we did a training, right, at one place. So for example, IIIT Allahabad. So we have around, say, for example, you have data sets of around 100 or 200. So we have given all the 200 data sets at one place, and then we computed the accuracy. And then we did it in a distributed way. In that way, what we really see is the results are on par. Though there's a small, very small variation in the performance, so which is comparable. And then we were able to achieve the sensitivity and the accuracy is on par with the standalone and as well as the distributed learning way. As a summary and next step, what we really want to do is, so we concept of fair data station we realized, and then hypothesis of enabling distributed learning using fair data station is also explored. So finally, what we are doing, extend the fair data concept to pilot in network hospitals to build and validate models in a federated way. This work is happening. Yeah, Philips is also partnered with many clinical sites, and this work is in progress. This is in that way. The initial results are very encouraging. What we got. So similarly, we are working on developing multiple models this way. Okay, that's about it. Thank you. Thanks for the patient hearing. Then let's discuss. Is there any questions? And the session is open, and we can always discuss. Any questions? I saw some comments from in the chat section. Can anyone help me in reading that out, or let me open that?